What's up guys, it's Timon Fiaz and today's video is on AQA Level Chemistry 2018 Paper 2. Question 1, given an equation for the complete combustion of heptane in excess of oxygen C7H16 plus O2 to form CO2 plus H2O. I need 7 carbons on the right hand side, 8 here, and then just balance it out, 11 here. Heptane can be obtained from catalytic cracking. Identify suitable catalyst. Zeolite catalyst, obviously. Zeolite catalyst. Give an equation. Give one condition other than heat. Slight pressure, not high pressure. Remember, thermal cracking is high temperature, high pressure. Catalytic, high temperature, slight pressure. And then give equation for the catalytic cracking of one molecule of hexadecane. C16H34 to one molecule of heptane C7H16 plus one molecule of cyclohexane C6H12, and therefore the remaining product must be C3H6 and alkene. C16H34 heptane C7H16, use CnH2n plus 2. Cyclohexane C6H12 and one of the products C3H6. Alkenes can be used in free radical substitution to produce hydrogen alkanes. Give equations for the propagation steps in reaction: butane, methane, ethane, propane, butane, C4H10. But obviously I don't want to draw it like that. I want to write it down as CH3, CH2, CH3. No, CH3, CH2, CH2, CH3. So Cl dot plus CH3, CH2, CH2, CH3. Now I want 2-chlorobutane. So I want the chloro to be on the second carbon, right? So it's going to be CH3, CH2, CH, free radical, CH3, CH2, CH, free radical here, CH3 plus HCl. And then you've got what you just had before, CH3, CH2, CH, chlorine free radical here, CH3 plus Cl2 to form CH3, CH2, CCl, CH3, CH3, CH2, CH, no, CHCl, they've added it, CHCl, CH3 plus chlorine free radical. So in this question, firstly butane C4H10, then realize, well, I want 2-chlorobutane, so I need to draw it properly, like this formula, and then Cl free radical plus that to form this plus a HCl, and obviously because I want 2-chlorobutane, I want the free radical to be on the second carbon, not on the hydrogen, second carbon. Then add excess of chlorine, you form that. You don't swap the hydrogen with the Cl, you add the Cl on, so CH3, CH2, CH, Cl, CH3 plus chlorine free radical. Identify the radical produced from the CFC that's responsible for the depletion of ozone atmosphere, Cl dot. Explain with the aid of equation by a single radical can cause decomposition of many molecules of ozone. Cl dot plus O3, ClO dot plus O2, ClO dot plus O3, arrow 2O2 plus Cl dot. Now you just need to memorize this off by heart. And then the explanation, well, yeah, that the Cl dot is regenerated and causes a chain reaction in the decomposition of ozone. So let's say again, Cl dot is regenerated and causes a chain reaction in the decomposition of ozone. 10 marks. And this is a year 1 topic. And imagine you had this exam. You're doing your A-level chemistry paper 2 in 2018. One topic you didn't memorize, and 10 marks of it came up. Give a U-Pack name for CH2OH, CH3, CH2Br. So it's going to be 3-bromo, 2-methyl, propan 1-ol. Because you think about it, you've got one carbon here, one carbon here. That's your methyl group, and then that's the third carbon. 3-bromo. Because remember, alphabetical order A, B. That's before M in the alphabet. It's 3-bromo, then 2-methyl, because 2 the methyl groups in second carbon, and then propan. Why is it 1-ol? Because alcohol group is on the first carbon. So when you simplify it like that, then it makes sense. So 3-bromo, 2-methyl, propan 1-ol. Explain why the halogen alkanes attacked by the nucleophile in this reaction. Bromine is more electronegative than carbon. Carbon is partially positive / electron deficient lone pair of electrons and nucleophile donated to the partially positive carbon. Bromine is more electronegative than carbon. Carbon is partially positive / electron deficient. Lone pair of electrons and nucleophile donated to the partially positive carbon. Then it said draw the displayed formula of compound Y. Compound Y, C4H6O2. In this range, so C4H6O2, so bond O here, H here, hydrogen here. There you go, C4H6O2. Compound Z has a empirical formula this. Give the structure of compound Z. Empirical formula this. I want the structure of compound Z. So it's going to be NC CH HO CH3 HCCN, sorry, CCN OHN OHHN. It's just the reagent for reaction 3, KCN followed by dilute acid. Explain the reference to intermolecular formulas, molecular forces by distillation allows propanol to be separated in this reaction mixture. So aldehyde / propanol has dipole forces between molecules. Alcohol / in this case propan 1-ol and propanoic acid / carboxylic acid have hydrogen bonding between molecule. Forces between molecules in aldehyde are weaker than those in alcohol and carboxylic acid, hence aldehyde / propanol will evaporate first. Aldehyde / dipole has dipole force between molecules. Alcohol and propanoic acid has hydrogen bonding between molecules. Forces between molecules of aldehyde are weaker hence aldehyde slash propanol will evaporate first. Give two ways of maximizing the yield obtained by distillation of reaction mixture. Keep the temperature of the reaction mixture below boiling point of propanol, and it tells us 97 degrees, so below 97 degrees Celsius. Keep temperature below boiling point propanol. Cool the distillate slash collecting vessel. Describe how you carry out simple test tube reaction to confirm the sample of aldehyde does not contain any propanolic acid. Sodium carbonate. So add sodium carbonate to a sample of distillate. Effervescence would confirm presence of acid. Therefore, if it does not contain any propanolic acid, it would not have effervescence. Then it says question 3.4, student carried out experiment to determine the enthalpy of combustion of ethanol. Alhamdulillah. So I want to find enthalpy of combustion. And I also need to use Q equals MC delta T. And I also need to use moles of mass of MR. So that's the first thing. Imagine you look at this question, you can't recall any of these equations. I don't know how you're going to attack the question. So first things first, I know, well, this case, this is for the mass of water, so I can find out Q very easily. Let's do that. Q equals 150 times by 4.18 given in a question, times by temperature change 40.2 minus 25.1. Now the moles equals mass of MR, but in this case the mass is of the ethanol. Obviously in grams, and I've got it in milligrams. Now to go from grams to milligrams, I times by 1,000, but I want to go from milligrams to grams, so I'm going to divide by 1,000. So it's going to be 0.457 over the MR of ethanol, and again I'm going to have to work that out. Well, ethanol, methane, ethane, and then your OH, so C2H, methane, ethane, H, C2H5OH. But anyway, I'll work out the MR. 12 plus 12 plus 1, 2, 3, 4, 5, 6 plus 16, 46. Then I'm going to use delta HHQ divided by moles, and I'm going to work out Q by just putting what I just put in the calculator. 150 times by 4.18 times by 40.2 minus 25.1. But I want it in kilojoules multiplied minus 1, so then I need to divide my answer by 1,000. 9.466 677 divided by 0.4457 divided by 0.457 divided by 46, and then I do 9.4677 divided by my answer, and I get 953. 153, perfect, and I'm done, right? I'm done. No, because I also know that the temperature increase went from 25.1 degrees Celsius to 40.2 degrees Celsius, so therefore I need to add this negative sign because temperature increased. Temperature increased. What does that tell me? Therefore, it's exothermic. Okay, question 3.5. Name an analog mechanism for the reaction producing pentwanine and the mechanism. Okay, this is going to be fun. So, pentantiol is dehydrated. So it is elimination. Last time I checked, yeah, elimination. And elimination of water from ethanol to form ethene. So in this case, elimination of water from pentantiol to form pentwanine. So first you draw out pentantiol: methane, ethane, propane, butane, pentane. Then what happens is you've got your H plus here, lone pair of electrons on OH, bonds to this H plus, and then what happens is, I'm trying to recall it now, then the okay, then the oxygen is positively charged, so then I've got obviously this as well. Last time I checked, the oxygen positive charge. So yeah, oxygen positive charge. Bunch of two H's here. And then what happens is you've got your carbon cation here. This leaves as H2O. And then what happens is you've got this, and now this carbon positive charge, CH3, this OHH left as water. And then what happens is it wants to form a double bond, but I want to form pentwanine. So then it goes here, you form your double bond, and then you lose your H plus. Perfect. So that bonds to H plus goes to there, and then yeah, that final arrow, and then you get the alkene, which I'm not going to go through because all you're doing is you form the double bond and you lose a H plus. So then plus H plus, as long as you plus H2O. Again, how well you know your mechanisms. Nice 4 marks by just literally memorization. 3.6 stereoisomers is also formed in this question. In reaction question 3.5, name the less polar stereoisomer formed. E-pent-2ene, E-pent-2ene. Explain how the type of stereoisomerism arises. Carbon-carbon bond cannot rotate, and each carbon in the double bond has 2 different groups attached. Carbon-carbon bond cannot rotate, therefore it's E, and each carbon in the double has 2 different groups attached. Question 4. What is this? It says a B could contain this much that of A, then this much of B and this much add to B can mix after each equilibrium. The mixture contains this much of moles of A. Calculate moles of B and C and D in equilibrium mixture. Now, what you notice with paper 1, in paper 1, the kind of topics like KC are pretty straightforward, like textbook examples. But with paper 2, they just do it in unfamiliar ways, which is fine because generally they're easier. You just need to spot what you need to do. These maths kind of calculation questions, A, B, C, and D. I'm just going to use ICE method, initial moles, changing moles, equilibrium moles. And I know initially I've got 40 centimeters cubed with this. So first thing I'm going to have to do is calculate the moles of that. moles concentration of volume, 6.4 times by 10 to the power minus 3, and that's of A. Of B, initially 9.5 times by 10 to the power minus 3. Of C, 2.8 times by 10 to the power minus 2. Mixture left each equilibrium. Equilibrium mixture contain this much of A, so 3.9 times by 10 to the power minus 3 moles, equilibrium moles of A. So how have I gone from here to here? Well, all I'm going to have to do is 6.4 times by 10 to the power minus 3 minus 3.9 times by 10 to the power minus 3. 6.4 minus 3.9. 6.4 times by 10 to the power minus 3. Initial amount of moles of A, 6.4 times by 10 to the power minus 3. The equilibrium mixture formed contained this much moles of A. That much moles of A. Perfect. So I'm going to say minus actually I'm going to use it. Okay, so 6.4 times by 10 to the power minus 3. How do I get to there? 6.4 times by 10 times by 10 to the power minus 3 minus 3.9 times by 10 to the power minus 3. And minus 2.5 times by 10 to the power minus 3. And obviously this is a 2 to 1 mole ratio. If I'm minusing that much here, I'm going to minus 1.25 times by 10 to the power minus 3 here. I just divided by 2. So 9.5 times by 10 to the power minus 3 minus 2.5 times by 10 to the power minus 3 divided by 2. 8.25 times by 10 to the power minus 3. And then here for C, well, that's a 2 to 3 mole ratio. So then I'm going to do 2.5 times by 10 to the power minus 3 divided by 2 and then times by 3 and then do 2.8 times by 10 to the power minus 2 plus that. And I get 0.0318. And therefore for D it's just going to be that divided by 3, 0.0. Actually no, it's not, because with D I start off initially 0, I add something to get to the final one, but I'm just adding 1.25 times by 10 to the power minus 3. So for B it is 8.25 times by 10 to the power minus 3. For C it is 0.0318, and for D it is 1.25 times by 10 to the power minus 3. Be aware of the mole ratios, and yeah, that's really it. And also don't be fooled like I fell for it, that just because you've got something here initially doesn't mean you always have to subtract it, because on the left hand side I'm subtracting, on the right hand side I'm adding. Even though initially I've got this much moles of C, I'm still adding to it. Don't subtract here and then add for D, where you have to add for both, because that's on the different right hand side compared to left hand side we're subtracting. Give an expression for KC. KC is square brackets plus equilibrium square brackets of C cubed, because I've got 3 moles of it, D divided by A squared B. The units, well, I'm working with moles per dm minus cubed, so it's just going to be moles per dm minus cubed to power 4 over moles per dm minus cubed to power 3. That cancels out and I'm just left with moles per dm minus cubed. Question 4.3. Blah blah blah. Different equilibrium mixture can this much moles of B, C, and D. Total volume of that. Temperature numerical value of Kc was that. Calculate concentration of A. So first thing I would do is rearrange it to find concentration of A. So all I'm going to do is concentration of A equals concentration of C cubed times by concentration of D divided by Kc times by concentration of B, and then square root the whole thing. Yeah, that's all I'm doing. Just rearrange it and square root the whole thing. C cubed, well, C is 1.05 cubed times by 0.076 divided by Kc, which is 116, times by B, which is 0.21. And the volumes, well, the volumes cancel out. So yeah, obviously in the exam I would show that, but don't need to waste time for this video. The volumes will cancel out anyway. What's that? 0.21. And then square root my answer, obviously. No. Okay, wait. I've done something wrong clearly. So actually the volumes won't cancel out because I've got Kc here. So if volumes cancel out, this Kc would be, so I actually do have to include the volumes. 5.0 times by 10 to the power 2. Well, then I want it in moles per dm minus cubed, so that's going to be 0.5. Oh, that is really sneaky. And I fell for it. So it's going to be square root of 1.05 divided by 0.5 cubed times by 0.076 divided by 0.5 by 116 times by 0.21 divided by 0.5, and then you get 0.17. And yeah, you do have to include volumes because of Kc, because you can't just cancel out volume Kc because Kc is not with volume, so you do have to include volumes. Justify the statement that adding more water to equilibrium mixture in question 4.3 will lower the amount of A in the mixture. Add more water. Same as with like pressure, if I add more, it's going to shift to the side with fewer. If I justify the statement adding more water will lower the amount, adding more water or concentration for equilibrium, because if I add more water into the reaction mixture then left to reach equilibrium, and the total volume of that equilibrium shifts this side with more moles to oppose the decrease and concentration. Because you have to remember, moles is concentration and volume. Concentration is moles divided by volume. So if I'm adding more water, the concentration will definitely fall. All the concentrations will fall. Equilibrium shifts aside the fume with more moles of gas to oppose a decrease. Concentration. Question 5. Use data from experiment 1 to calculate value for rate constant K. Calculate value for rate constant K at this temperature and give its units. It doesn't want me to, it does want me to complete table 2, 5.2, but data from experiment 1. So, rate constant K, so K equals the rate divided by BR O3 minus BR concentration H plus squared, and then I just substitute the values in. It's that simple. Obviously, show you working out in the exam, but this case, there's just no point of me doing it because I've just shown you guys the equation. So 2.4 times by 10 to the power minus 2 divided by 0.10 times by 0.20 times by 0.30, but with 0.30 it is squared if I look there because H plus squared. That will give me 13.5. It's 2.4 times by 10 to the power minus 2. Why did I get 2.43 from? I get 13.33. 13. The units, well, I've got moles per dm minus cubed s power minus 1 over moles per dm minus cubed 1, 2, 3, 4 dm minus cubed to power 4. That cancels out. I've got s power minus 1 over moles per dm minus cubed. That's the same as s to the power minus 1 over mol to the power 3 dm to the power minus 9, and that is the same as s to the power minus 1 mol to the power minus 3 dm to the power 9. Okay, and then 5.2, complete table 2. I feel like this part's going to be harder than the first part. Completing table 2. This stays the same, that stays the same. What happens to this? Well, 3.6 times by 10 to the power minus 2 divided by 2.4 times by 10 to the power minus 2. And timesing by 1.5. What's going to happen to this? I'm going to just times by 1.5. Very simple. But then the other parts, this part's going to be harder, 2 to 3. Well, here I'm going from 0.15 to 0.20, so I'm times it by 4 over 3. Here I'm timesing by 2. Here I'm timesing by 5 over 3. And I know h plus squared, so it's going to be 4 over 3 times by 2, 4 over 3 times by 2 times by 5 over 3, but the 5 over 3 is squared, and then do 3.6 times by 10 to the power minus 2 times by my answer to get 0.27. Just don't forget that it's squared. Then to go from here to here, 0.20 divided by 0.10 times it by 2. No, I'm not. 0.10 divided by 0.2. I'm times it by a half. times it by a half. Here I'm times it by a quarter. Here I don't know what I'm times it by. 2.7 down by 10 to the power minus 2 divided by 0.27. 1 over 10 times it by 1 over 10. So then a half times by 1 over 4, 1 over 8. 1 over 8 times by something squared to give me 1 over 10. That's basically what the expression is. So 1 over 10 divided by 1 over 8. And then square root my answer. And then that's the factor I'm going to be timesing by, and then do 0.50 times by my answer to get 0.45. You can see how it's just like so many steps. 0.45. 5.3. Complete table 3. This is very easy. Just do 1 over t. So 1 over capital T. So 1 over 286, for example, would give you 3.50 times. So 1 over 3 over 2. 302. 3.31 times by 10 to the power minus 3. And then ln 1 over t ln. Yeah. Minus 3.30. Then it says, okay, got this, can written as this, therefore this. Use values from table 3 to plot a graph of ln 1 over t. So I'm plotting this against 1 over t on the grid. So then that's 1 over t, plot ln 1 over t, you know, just plot it x-axis, y-axis. But then it says, then use your graph to calculate value for activation energy, including small to power minus 1 for this reaction. So just plot it. I'm just going to do a quick one, minus 2. I'm definitely not accurate, but just don't waste time. Minus 2.8, minus 3.2, minus 3.6, minus 4.0, and increase by 2. 2. And then what you should notice is that obviously label that ln 1 over t, and then should be like a straight line down. And it definitely should be a straight line. The reason being is because with these Arrhenius calculation questions and equations and all of this, we have to compare it to y equals mx plus c. That's what we're going to do now. And if we do that, y is that, x is that, c is that. I want to find out activation energy, which is the gradient. Well, the gradient I can see is minus EA over R. And that's why it has to be a straight line, either downwards or upwards, or I don't know, even sideways, but it has to be a straight line because you have to compare it to y equals mx plus c. Then rearrange it, minus EA equals the gradient times by R. We work out the gradient, y2 minus y1 over x2 minus x1 times by 8.31. And then divide by minus 1 to calculate EA as 55.2 kilojoules per mole to the power minus 1. And there we go. So it did look like a really extremely difficult question, but in reality, 1, 2, 3 marks are for plotting your points. So half the marks are plotting the points. Then the 4th mark is for identifying gradients minus EA over R and finding out the gradient, rearranging it to find EA, and then the final mark for the answer. So not that difficult. Explain the bonding in the shape of benzene molecule. So stage 1 bonding. Each carbon has 3 covalent bonds. Spare electrons in a p orbital overlap to form a pi cloud delocalization. Stage 2 shape, planar, hexagon / 6 carbon ring and 120-degree bond angle. Carbon-carbon bonds equal in length. Stage 3 stability. Expected enthalpy of hydrogenation of cyclohexatriene is minus 360 kilojoules mole to power minus 1. Enthalpy of hydrogenation of benzene is less exothermic by 152 kilojoules mole to power minus 1. Benzene is the more stable. Okay, benzene is lower in energy than cyclohexatriene. Stage 1 bonding. Each carbon has 3 covalent bonds. Spare electrons p orbital overlap to form a pi cloud. Should be like that, pi cloud. Each carbon has 2 covalent bonds. Spare electrons p orbital overlap to form a pi cloud. Delocalization. Stage 2 shape, planar shape, hexagon / 6 carbon rings and 120-degree bond angle. Carbon-carbon bonds equal in length. Stage 3 stability. Expected enthalpy of hydrogenation is that. Enthalpy of hydrogenation of benzene is that. Exothermic by 152 kilojoules mole to power minus 1. Benzene is more stable, aka benzene is lower in energy than cyclohexatriene. Enthalpy is not exactly double that of cyclohexene. Suggested value minus 239. Double bonds are separated by one single bond, or we can say the alternating, hence allows for some delocalization / overlap of p orbitals. And with benzene and this topic in general of aromatic amine and benzene, this question is very, very common, very classic. Compare the bonding, compare the stability, explain the bonding of shape of benzene, and then obviously electrophilic substitution mechanism and nitration, acylation, and then that's really it, to be honest. So yeah, minus 239. Double bonds are separated by one single bond / alternating, hence allows for some delocalization / overlap of p orbitals. Given the equation for reaction of this with AlCl3 to form the electrophile, it is going to be, given equation, I thought it said, name the mechanism, CH3 CH2 COCl plus AlCl3 to form CH3 CH2 C double bond O carbon positive charge plus AlCl4 minus CH2 CH2 COCl plus AlCl3 arrow CH3 CH2 C double bond O positive charge carbon plus AlCl4 minus. Mechanism of electrophile with benzene. Again, benzene electrophilic substitution mechanism. So electrophile, so CO CH2 CH3 positive charge carbon. Here you go. Boom. Partial horseshoe ring, so something like that. Positive charge here. Got hydrogen here. I've got my CO CH2 CH3 here. Boom, goes there. And then CO CH2 CH3. They always like asking about electrophilic substitution mechanism, and you should literally know mechanisms like so well. Like you can just literally do it to apply it to any compound. So the equation CH3CH2Cl, opposite AlCl3, arrow CH3CH2C, double bond O, carbon positive charge, plus AlCl4 minus. Here's the mechanism, there, and then there, and then you form that. Give the IUPAC name of the alcohol. So it's going to be 1-phenyl propan-2-ol. 1-phenyl, is it, wait, 1-phenyl propan, is it 2-ol? No, it's 1-ol. 1-phenyl propan-1-ol. The reagent needed for this reaction. The organic product in question 7.1. So this can be converted into the alcohol. So it's going to be the reagent sodium borohydride and the name mechanism nucleophilic addition. Phenyl propan 1-ol sodium borohydride nucleophilic addition. Then it says describe what will be observed when the alcohol reacts with ethanol chloride. Misty fumes. Name the mechanism for the reaction to form the ester. Reacts with ethanol chloride to form ester and nucleophilic addition elimination. Nucleophilic addition dash elimination. Show the structure of the ester. Well, what's going to happen is nucleophilic addition elimination reacts with ethanol chloride, alcohol, ethanol chloride. We're going to have CH3, C double bond O, OCH, and then your CH2, CH3. Question 8. Explain how these hydrogen bonds form. So the idea that electron deficient hydrogen, which attracts the lone pair of electrons on oxygen. Very simple for 2 marks. Electron deficient hydrogen, which attracts a lone pair of electrons on oxygen. Complete the structure to the bond that forms between the side chains of 2 cytosine molecules. So I've got HC, and then I've also got CH2 cytosine. No, cytine. So I've got H2N. I've got the SH. In this case, it's going to be the S, and then the CH2S. There you go. Name is type of protein structure. Quaternary, or you could say tertiary, but I would always like to say quaternary. No, that's not how you spell it. Quaternary. Then it says draw the structure of the Zwitter ion of a dipeptide formed by alanine and serine. So alanine is a H2N CH CH3. Serine is, or serine, whatever you want to say, H2N CH CH2OH. Now what's going to happen is this and the hydrogen from here bonds to form your water molecule, and then because it's a Zwitter ion, I'm going to have a positive charge and negatively charged part. So it's going to be H3N plus CH CH3. Then obviously you've got the C double bond O, you've got your NH attached to it, that bonding, and then you've got your CHCOO minus, and then you've got your H2COH. So draw them out from your thingy table, your data sheet and the periodic table. Draw them out, and then remember they're going to bond together to form your dipeptide, C double bond O and your NH, and obviously there's Witter ions, so one positive charged part, one negatively charged part. And not too bad. In question 9, complete table 4 to show the correct sequence of bases in the complementary strands represented by the numbers 1 to 5. Alhamdulillah. So 1, T, G, C, A, G. The T1, yeah, T, G, C, A, and G. T, G, C, A, G. Deduce total number of hydrogen bonds formed between 5 bases in each strand. It's going to be 13 hydrogen bonds. Then it says, so TgCAg, 13 hydrogen bonds. Then it says complete structural nucleotide that contains base A. It contains a 2-deoxyribose nuclear molecule, an incomplete 2-deoxyribose nuclear molecule is here. So you've got your A here. You represent the base A by the letter A. Yeah, the base by letter A. A here, H here, H here, H here, H here, O here, and then your H here, and then it is polynucleotide CH2, and then it's gonna, and then you've got your phosphate, so you've got your P double bond O, O minus, O, oxygen bond to CH2. So 1 mark completed 2-deoxyribose plus A, and 1 mark for the correct phosphate joined to CH2. Question 10. Infrared spectra B, A, B, and C of those are primary amine, tertiary amine, and nitrile, but not necessarily in that order. Give the letter of each compound in the box. C for the primary amine, B for the tertiary amine, A for nitrile. George complete formulas of these 3 secondary amines, or justifies the statement as better to prepare primary amines from nitriles rather than halogen alkanes. It is, because with halogeno alkanes, a further reaction of primary amines. Hence, impure product / mixture of products. Whereas with nitriles, there's no further reaction, hence single product. So with halogen alkanes, further reaction of primary amines, hence impure product. That's what you have to say. The structure of a primary amine with 4 carbon atoms that cannot be formed from a nitrile. So H3C, CH, NH2, CH2, CH3. 1 to 3 cannot be formed from a nitrile. Then it says, given the equation reaction that occurs when propylamine CH3, CH2, CH2, NH2, your propyl group, then your amine, is added to water. It's going to be a reversible reaction, and what you're going to form is CH3, CH2, CH2, NH3 plus OH minus. Observation: because the green turns blue. Given the equation for the reaction of nitrobenzene to form phenyl, reduction of nitrobenzene to form phenyl alanine, C6H5NO2. Actually, I'm going to do it this way. This is the way that I've memorized it, and it should be fine in the exam. Your NO2 plus 6 H's to form your phenylalanine, with your NH2 group attached to it, plus 2H12. Then it says, explain why an aqueous solution is obtained even though it is insoluble in water. So the idea that the C6H5NH2, the aromatic amine, is present as an ionic salt, and therefore an aqueous solution is obtained because it's present ionic salt. Question 11 can't do, question 12 can't do, question 13 no, all 13 see NMR spectrum, haven't even started that. And that is the end of this past paper.